Section 1.7, Transformations of Functions. The first one we're going to look at as far as the graph transformations that we've done previously is shifting graphs. So this is basically a translation either vertically or horizontally. So first off, looking at the vertical aspect, that's essentially where you take a function and you add or subtract a number on the outside of it. Okay, so that means the y values are what you're adding or subtracting to, which of course moves the graph up or down. So the way that we want to remember, of course, is if we add, this is of course what makes the graph move, upward, and certainly down will happen if we subtract. Now remember, when we talk about, moving up or down or left or right or really any transformation, it's always how it changes from the parent graph. Okay, so just to be clear, like when I look at this graph, f of x equals x squared, the green graph is that parent graph that we of course have memorized. So by adding or subtracting a number to the outside, again, that changes the y values and moves the graph either up if you're adding or moves it down if you're subtracting. Now, the other one, of course, is moving left and right. So obviously moving left or right is adjusting x values, which means the inputs, as you can see here on the inside of the parentheses in function notation, the inputs are what are going to be changed. So if you're going to be shifting horizontally right, you will subtract numbers away from the x. And that just makes sense to correspond with where the x-intercept is. Likewise, if you want to shift the graph to the left, you will add numbers to the input. And again, in function notation, because this is being expressed inside the parentheses, it will happen before any other operation. So unlike the last one, moving up or down, where the last thing we did was add or subtract, here, the first thing we do is add or subtract. And again, based on the parent graph, moving to the left or the right, that's exactly what this looks like when adding or subtracting. Now, the last thing we're going to talk about, of course, is reflections. And in this case, I decided to choose a different graph, the square root of x, to help better illustrate what the reflections look like. Because in some graphs, when you reflect it, it may not look much different. So the first kind of reflection is in the x-axis. Okay, so this would kind of be a vertical idea that has the x-axis as your kind of symmetry, right? So if you put a negative on the outside, that of course is saying all the y values will take on the opposite sign. So all the y values in this original parent graph, if you will change signs to the negative, moving them down here below the x-axis. And therefore, because for every x we simply have an opposite y, the x-axis here gives us our symmetry. Now, if we want to reflect in the y-axis, we do the negative again, but this time to the input on the inside, because then of course what's happening is we're taking the x values, changing those right away, and that reflects and has the y-axis vertically here be your symmetry line. So that would reflect it horizontally. Now the last piece after translations and reflections is stretches and shrinks. Now essentially this doesn't really move the graph around, but instead expands it or contracts it kind of depending on which way you're going. So the first thing to look at, of course, are vertical shrinks. Okay, so vertical just means, if you stretch vertically, you become more vertical. If you shrink, and I should point out, this should say shrink, because this is not stretch. Because we say away, we're going to say this is a shrink. There we go. So obviously, if your a value, the number that you're multiplying by, if you multiply your y values by anything bigger than 1, it will stretch it toward the y-axis. And another way of thinking about that is, from our parent graph here, and I'm using the example of the absolute value, we make it more vertical, right? Because we're multiplying on the outside, because the y values get multiplied, they get bigger faster. So it just becomes, stretched closer toward the y-axis. Now, likewise, if you multiply on the outside, and the number, of course, is going to be between 0 and 1, like a half or a third or 2/5 or something that's between 0 and 1, what happens in that case then is it shrinks it away from where from the y-axis, because it kind of slows down how vertical it gets, because you're only taking a number this may be a third as much or 3/8 as much, something that's between 0 and 1. So when you stretch vertically, you get more vertical, you're toward the x-axis. When you shrink vertically, again, you're moving kind of away from the y-axis and getting steeper, slower. Now, a different way of looking at it is horizontal stretches and shrinks. Now, this, of course, is where you'll be dealing with the input. Now, on this one, of course, when you do it, you're going to have your function, right? Except this time, you're going to be dealing with a number on the inside multiplied by x. Now, this number here on the inside doesn't behave exactly the same as the vertical ones. And what I mean by that, of course, is that on the inside, what's going to happen is it's either going to stretch or shrink, right, from the x-axis. So it either gets closer to the x-axis, more horizontal, that'll be a stretch, or it'll shrink away from the x-axis, become less horizontal. But it always does it by the reciprocal amount. So if this a value here was like, say, a 5, then what would be happening is, of course, that's going to be shrinking away because it's moving away at 1/5. Likewise, if the number a here was like a 1/2, then it would be stretching because, again, it would be stretching toward, because, again, it behaves as a reciprocal, so 1/2 would be like a 2. So it's kind of an opposite feel. So when you want to stretch things and make them more horizontal, you have to put fractions in here, right? So if I want to stretch it by 2, you got to put a 1/2 in there. If I want to do a horizontal shrink by, let's say, 1/5, I got to put a 5 in here, okay? Because it will always behave in the reciprocal manner. So let's try this out. Now, the things we want you to be able to do, of course, are, first off, identify the parent function. So just by looking at g of x here, what's our parent? We're going to call it f of x, but what, memorized graph does this come from? The second thing, of course, are what are the transformations that are happening? Okay, so from the parent graph, how are we moving it around to create this new function g? And of course, the last thing we want to be able to do is let's rewrite g of x using f of x, using the parent function. And really, that's just taking the idea of the transformations and really write them in function notation to illustrate what's happening. Okay, so in our first one here, let's just start with our parent graph. All right, so first off, when you see a quantity squared and some stuff on the inside outside, clearly it's going to be that quadratic, right? F of x equals x squared. Now, as far as our transformations, on the inside, we're subtracting 1. On the outside, we're subtracting 2. So on the inside, when you subtract, that moves you right. Okay? Things on the inside tend to always kind of work in the opposite way that you expect sometimes. So that's going to go right 1. And then, of course, on the outside, because we're subtracting the 2, that means we're going to go down 2. Now, our last step, of course, is to write this in terms of f of x, right? So obviously, we've named this brand new function here g of x. But what we want to do is write it in terms of f of x. So instead of talking about it explicitly like this, we want to say, well, if f of x is our parent graph, what would that look like? Well, because we moved right 1 on the inside, right, we're going to be subtracting 1. And then outside the function, we'll be subtracting 2. So it's going to have the same look and feel almost as what the original function looks like, but in place of the idea of squaring a quantity in this case, we're going to replace that with f of x, as that's what the parent graph is. Now, when we look at actually sketching it, okay, we want to go ahead and do the same properties, right? We're going to basically draw x squared, right? Again, the graph we've memorized, but we're going to move it right 1 and down 2. So starting at the origin, where the parent graph normally is, I'm going to move right 1, down 2, and make a dot. Okay, that's going to be where my vertex is. And then from there, I just need to graph a regular parabola. Because, again, the only thing going on in this graph is simply moving right, moving down. So the parent graph x squared, now that it's moved, still goes over 1 up 1. And then you return back to the starting place, and you count over 2 up 4. That's always the pattern for parabolas. We're going to reflect those dots over to the other side. And there we go. And all we got to do at this point in time then is take those dots and help us sketch that parabola. Okay, so again, it's just like our parent graph, except this one, as you can see, is right 1, down 2. Let's try it again. This time we're going to do it with a radical graph. So in our radical graph here, again, we have to identify the parent graph, and that, of course, would be the square root of x. Now, as far as the transformations, we got 3 of them. So the first thing I noticed right away is on the inside, we're adding 3. Okay, so that means we're going to take the graph and go left 3. The second thing I noticed is that we have a negative 2 on the outside. But remember, the negative is a reflection, the 2 is a vertical stretch. So this counts as 2 different transformations because the negative essentially reflects it in the x-axis because, again, it's on the outside, it's a vertical change. And the 2 is basically going to do the kind of stretch it more toward the y-axis, right? It's that vertical stretch by a factor of 2. So after this, I'm just going to go ahead and write the negative first and say we're going to have a reflection in the x-axis. And then we're going to do a vertical stretch by a factor of 2. Okay, and of course the last thing we want to do is rewrite, in this case, our function here in terms of, of the f of x stuff. So our our function here is going to be basically negative 2 on the outside. We're multiplying that by the function, and the input is changed by plus 3. And again, one of the benefits of writing in function notation is you really get a sense of the horizontal and the vertical changes. All the things that go on inside the parentheses, those are horizontal changes because they're inputs. And anything that you're doing on the outside to the function f of x, of course, is changing the y values. And so those are vertical changes. Okay, so let's go ahead and graph this. Now again, the parent graph typically is going to be at, or we should say beginning at the origin. But this graph, of course, as far as left and right and up and down, it gets moved left 3. So as far as any translations, that's it. So I'm going to count 3 to the left and make a dot. Now, unlike the regular square root graph, where maybe I would count over 1 up 1 and over 4 up 2 to give me a couple points to draw through, I've got to make 2 changes. Of course, number 1, we're going to go the opposite direction vertically. Okay, this negative out front means that instead of going up, we're going to go down. So we're reflected in the x-axis. Now, at the same time that I'm going to go down instead of up, I also have to double how far vertically I go. Now, I'm still going to go over 1. I'm still going to go over 4. But I need to double how far down I go because the vertical component's double. So I'm going down because it's negative, and I'm going twice as far because of the 2. So normally from this point I would go over 1 up 1, but I'm going to go over 1 down twice that much 2. Okay, then I return to the original starting point. And normally I would count over 4 and up 2, but now of course after going over 4 I'm going to go down twice as much, down 4. And that should give me enough to go ahead and sketch it. So here would be the square root graph that is again left 3 and then reflecting the x-axis and vertically stretched by 2. Now that we've talked about graphing and looking and identifying transformations, let's work on looking at transformations and writing the equation. So first off, we have to give our equation a name. So I'm just going to go ahead and call this f of x. And it's important as we read through this to make sure we understand the order. In this case, what happened to the parent graph x cubed is that first it's shifted 6 units left, then 6 units down, and lastly it's reflected in the y-axis. That's important because we want the order of operations to reflect that. So what we're going to do first is make the 6 units left. We have to give ourselves parentheses and make sure, of course, if we're going left, we add 6. Okay? And again, notice how I had to add these parentheses around there because when we talk about going left, that's on the inside. And, as the parent graph is written here, we don't have really any grouping symbols. So you may have to give yourself parentheses to ensure that the plus 6 happens before the operation, in this case, cubed. The next thing that happens is we're going to go 6 units down. So on the outside, we're going to subtract 6. Okay, so we can see that we're going 6 left and 6 down. But the last thing that needs to happen then, it needs to be reflected in the y-axis. So that means that we need to go to the inside and make the inside negative. But remember, the inside already has an x plus 6 here. So we have to make all of it negative. Right? So I have to make a negative and put the parentheses there to imply the negative goes to each one. So we can actually simplify this and make it look like, when I distribute my negative here on the inside, negative x minus 6 cubed minus 6. Okay? So the order of operations is important here, and more importantly, when you simplify it, you have to understand where it comes from. So one thing you want to keep in mind, especially when you're maybe reading an equation and trying to identify transformations, is if your x doesn't have a coefficient of a 1, like this one, consider factoring out and getting that to happen. So if you're given something that looks like this, factor the negative out, make it look like this. Because now you can clearly see that it is in fact left 6 with a reflection and down 6, whereas here you might mistakenly think that there's a reflection and then right 6, which would be incorrect. All right, let's try one more with a new parent function, the absolute value. Right, so in this case we'll make it kind of in general. We'll just put an a in there. But again, we want to shift 4 units to the left and then 8 units down. So again, we'll give our function a brand new name. I'll call it f of x. On the inside, we're going to go ahead and add 4 to move it 4 left. And on the outside, we're going to subtract 8 to shift down 8.